Welcome back to our next section on our Chapter 3 lecture in Applied Statistics and Probability for Engineers. We're going to continue our discussion then about probability distributions. Before we move on to cumulative distribution functions, I just want to give you a brief recap. So a PDF, or a probability distribution function, looks like this. The probability of a random variable equaling one value gives me the probability of something, right? Which we said is little f of x. Okay, so our y value is our probability. So with the CDF, or a cumulative distribution function, we're then going to use a capital F. And the capital F this time denotes a cumulative value. And a cumulative value then is all numbers before it added together, right? So it's a kind of a comprehensive value, or cumulative, meaning things are added up as you go. So over here I have p of x, or p of a random variable equaling a value, is going to be less than or equal to some number. And this then is part of my cumulative definition, meaning it's added as we go. So keep in mind, the cumulative value is that my random variable is less than or equal to some number rather than equal. So based on these two definitions, we can see that my capital F of x, or my cumulative distribution function, is not equal to, or not always equal to, f of x, or the probability of my probability density function. So we'll see some examples in just a minute, but I just want you to review this and keep this in mind. The cumulative distribution function of a discrete random variable is as follows. So I have this, the probability of x, or f of x, capital F of x for a CDF, is equal to f of x equaling a value, which is equal to the summation of all x values less than or equal to the value that I'm looking at. So just keep in mind, we're going to be summing up all values less than the one that we're looking at. So now I have these definitions for a random variable x within a cumulative distribution function, or a CDF. So I have f of x equals the probability of x being less than or equal to a value equals the summation of all other probabilities, or see this right here, the probability distribution function f of x. So we're going to add up all of those probabilities as we go. So then once again, this is the same as the PDF, or the probability distribution function. My probability has to be between 0 and 1. And then my last property is that if x is less than or equal to y, then f of x is less than or equal to f of y. And this just means then, if you look at a graph of cumulative values being added as you go, this then just states that probabilities get bigger as you go on, right? Because I keep adding them to the other probabilities. Okay, so this right here, a cumulative distribution function, is built from a probability mass function and vice versa. So this right here is one of the key aspects to get out of this chapter, is that with a cumulative distribution function, I can find a probability mass function or a probability distribution function, and vice versa. So from a probability mass function or probability distribution function, I can also find a cumulative distribution function. And we'll look at both of these. So let's look at some examples that will help maybe solidify this. So given the probability distribution for x, find the cumulative distribution and find the probability that x is less than or equal to 4.5, greater than 4.5, and the probability that x is between 1.5 and less than or equal to 4.5. Okay, so I am given this probability distribution. And remember, a probability distribution is just a list of x values within a random variable and their corresponding probabilities. Okay, so I know that a cumulative distribution function then is just my probabilities added together. So I'm going to go through and do that. So at x equals 1, I have a cumulative distribution value, or probability, of 0.2. At 2, I'm going to add together the values less than or equal to that value. So I'm going to add together 0.5 and 0.2 to get 0.7. Then for 4, I'm going to add up everything less than that, so this, and this, which gives me a probability of 1. Okay, so then I'm going to graph that. So cumulative distribution functions are often piecewise functions, if you guys remember these. So if I go to graph this, I'm going to say that x is going to be 1, 2, and 4. So 1, 2, and 4. And I'm going to say for any value less than or equal to 1, I'm going to be at 0.2. Okay, so I graph 0.2. So notice I include the number 1 in this graph. Okay, so then at x equals 2, I have 0.7. So I'm going to come up here and say this is 0.7, but keep in mind between 1 and 2 it's also 0.7. So I don't include it here, but I do include that point here. At x equals 4, I have the number 1. So x equals 4, I include the number 1, and I have that all the way down to 2 over here, but not including 2. So that's what a graph of this cumulative distribution function would look like, okay? So notice I have x on my x-axis, and then I have capital F of x, which is my cumulative distribution function on my y-axis. Okay, so a way to write this cumulative distribution function then would be to write it like a piecewise function. So I would come in here and pretty much just write out what I see in my graph. You don't have to graph it every time in order to get your cumulative distribution function, but for me I feel like visualizing it, that step in between actually helps. Okay, so I'm going to say for x values less than or equal to 1, I have 0.2. For x values between 2 and 1, so notice I don't include the number 1 here, but I do include the number 2 here, I'm going to be at 0.7. Okay, and then for x values ranging between 2 and 4, but not including 2, my value is going to be at 1. So this piecewise function written out like this is my cumulative distribution function. So notice it's a capital F of x, and then I have my probabilities, and then their associated x values. Okay, so now that I have found the cumulative distribution function, I was also asked to find those individual probabilities. So I wrote up here, remember that the definition of a cumulative distribution function is this right here. So the definition is that my cumulative distribution function is equal to the probability that my random variable is less than or equal to the number in question. Whatever we are asked to find, that's what I'm going to put there. Okay, so first we're asked to find the probability that x is less than or equal to 4.5. Okay, so I'm going to come in here and I'm going to use this cumulative distribution line down here to answer my questions. Okay, so the probability that x is less than or equal to 4.5. Okay, so using its definition, I'm going to come in here and say the probability that x is less than or equal to 4.5. So does that look familiar to this, right? X is less than or equal to 4.5. That's the same as finding the cumulative distribution of 4.5. So if I come over here, the cumulative distribution of 4.5, which I don't have any probabilities for, but I can't really get higher than the number 1, so that number 1 then would just extend forward this way. So I would just say the probability or the cumulative distribution of 4.5 would equal the number 1. Okay, so now I would say find the probability that x is greater than 4.5, and I would just write it out this way. So remember our complements that we kind of introduced last chapter? So I have when x is greater than 4.5, that's the same thing as its complement, which would be 1 minus the probability that x is less than or equal to 4.5. So this is handy. We already found this probability. So if I write that out, it's going to look like this. 1 minus, and we just found that this probability is equal to 1. So 1 minus 1 equals 0. So the probability that x is going to be greater than 4.5, that probability then would be 0. And you can kind of look at that like I'm not going to have any number beyond 4.5, or I'm not going to have any probability beyond 4.5, so that makes sense that that's 0. So my next probability I'm asked is to find it when x is between 1.5 and 4.5. So when x is greater than 1.5 and when x is less than or equal to 4.5. So let's break that up. So this portion right here, according to my definition, is just going to be to find the cumulative distribution of 4.5, right? So then if I just subtract out this probability, the cumulative distribution of 1.5, so that's kind of like adding 1 minus the probability of 1.5, then I would just write that out like this. So I know that the probability of x being less than or equal to 1.5 is 0.2. So see right here, x being less than 1.5. I don't have a 1.5, I just have a 1 and a 2. So being less than or equal to 1.5 would just give me a 0.2 cumulative distribution probability. So that's what that would equal. So then I would subtract that out like that, and I would get the probability that x is between those two values would be 0.8. Okay, so that's an example on how when we're given a probability distribution function, how to come up with a cumulative distribution function and its corresponding probabilities. Okay, so now let's say determine the probability mass function of x from this cumulative distribution function. So now we're going backwards. We're given the cumulative distribution function and we want to get a probability mass function. Okay, so I'm going to graph this CDF. So I'm going to take all of these values and graph them on a piecewise function again. So here I have when x is less than 2, it's at 0. X is less than 2, I'm at 0. When x is between -2 and 0, I graph it like this. So notice this point is inclusive according to this, and this point is not. So keep that in mind as you graph. And then again here when it's between 0 and +2, I'm at 0.7. And when x is greater than or equal to 2, I am at +1. So if you notice, in theory, your last point should always be 1 on a cumulative distribution function because you want all of your probabilities to total 1, right? Okay, so my probability mass function then is going to be the difference in each of these vertically, right? Because remember, to get my cumulative distribution function, I added probabilities together as I went. Well, now I'm going to go and do the opposite. I'm going to find out what the difference is between here and here, and that will give me that probability, and differences between here and here, etc. So I say the probability of x equaling 2 is going to be 1 minus 0.7. That gives me that step, or that increment. So the probability there is going to be 0.3. The probability of x equaling 0, so notice I'm using lowercase f's this time because I'm coming up with the probability mass function or probability distribution function, is 0.5. The probability of x equaling 0.2 is going to be 0.2 because that's the difference there. Okay, so to write this in like formal probability distribution way would look like this. My x values are -2, 0, and 2. Y values or probability values of 0.2, 0.5, and 0.3. Okay, so that's how we would kind of do the opposite. So given a cumulative distribution function, how we would come up with a probability density function. So that's it for this section so far.